Difference between TSI-3B and TSI-3C. Post-stroke physiological perspective. Number 1694. VPT 139. June 22, 2026. Gerald C. EclaireMD Foundation. Category: Stroke. Preface for readers: eat more protein and fresh vegetables. Eat less red meat and processed food. Exercise daily. Walk as much as your physical condition allows. Drink sufficient water every day. Sleep adequately and consistently. Protect your emotional health. Avoid unnecessary stress and conflicts. Most importantly, continue learning. Knowledge is one of the most powerful tools available for protecting health and extending life. Introduction. During my continuing study of stroke recovery, I have developed several variations of the TSI stroke triggering sensitivity index to evaluate different aspects of stroke's pathophysiological stress. Among these, TSI-3B and TSI-3C are closely related because both use the same blood pressure components and differ primarily in the glucose input variable. Recently, I noticed that during the past 6 months, TSI-3C has remained consistently higher than TSI-3B. This observation initially raised an important question: does a higher TSI-3C indicate an increase in stroke risk, or is there another explanation? After examining the mathematics of the model, the physical characteristics of moving averages, and my post-stroke physiological data, I believe the answer is relatively straightforward. The difference between TSI-3B and TSI-3C appears to reflect the different response speeds of the two indices combined with a persistent post-stroke elevation in glucose levels. TSI-3B and TSI-3C measure the same system. Both TSI-3B and TSI-3C are derived from the same underlying pathophysiological framework. They contain the same blood pressure variables, and therefore evaluate the same cardiovascular system. The primary distinction lies in how glucose is represented. TSI-3B uses daily average glucose values. As a result, it responds relatively quickly to recent physiological changes. TSI-3C uses a 90-day moving average glucose value. This causes it to respond much more slowly because it incorporates the influence of approximately 3 months of prior data. Therefore, these two indices describe the same pathophysiological system but from different time perspectives. Fast variable versus slow variable. From an engineering viewpoint, I view TSI-3B as a fast state variable and TSI-3C as a slow state variable. The fast variable reflects what is happening now. The slow variable reflects what the system has been carrying over the previous 3 months. This distinction is similar to many physical systems where fast and slow dynamics coexist. Engineers routinely encounter such behavior in electrical circuits, control systems, structural vibrations, and thermal systems. The same principle appears to apply here. When glucose improves, TSI-3B responds first because it receives the updated daily data immediately. TSI-3C responds more slowly because the 90-day averaging process retains the memory of earlier values. For this reason, a lag between the two curves is not only expected but mathematically unavoidable. The influence of post-stroke glucose elevation. A second factor contributes to the difference between TSI-3B and TSI-3C. Since my hemorrhagic pontine stroke on June 21, 2025, I have consistently observed higher glucose levels compared with the pre-stroke period, most likely related to the increased metabolic demands associated with neuroplasticity and the brain's ongoing repair and recovery processes. Multiple analyses indicate that my post-stroke daily average glucose has remained approximately 10% to 11% higher than before the stroke. This shift has appeared repeatedly in several independent observations: higher daily average glucose, higher post-meal glucose peaks, broader glucose plateau duration, the development of a Tibetan plateau glucose profile rather than the sharper peaks observed before the stroke. The exact mechanism remains uncertain. Possible explanations include neuroplasticity, altered autonomic regulation, recovery-related energy demands, medication effects, or a combination of several pathophysiological factors. However, regardless of the mechanism, the existence of the glucose shift itself is clearly visible within the data, because TSI-3C incorporates a 90-day moving average glucose. It naturally retains the influence of this elevated post-stroke glucose environment. Therefore, it is expected that TSI-3C remains somewhat higher than TSI-3B even when more recent glucose values stabilized or improved. What the current data show, the current averages are approximately TSI-3C equals 99.23, TSI-3B equals 97.18. The TSI stroke difference is approximately 2 points. This separation is relatively small. If the gap were substantially larger, it could suggest a more significant mismatch between recent conditions and long-term physiological trends. Instead, the observed difference appears consistent with both the mathematics of the moving average process and the documented post-stroke glucose elevation. The relationship therefore appears internally consistent rather than abnormal. Comparison with the stroke period. Perhaps the most important observation is that neither TSI-3B nor TSI-3C is approaching the level observed during the stroke period of June-July of 2025. Before the stroke, TSI-3C reached approximately 109.1. The current TSI-3C value is approximately 99.2. This places the current level roughly 10 points below the pre-stroke peak. From the perspective of the TSI stroke model, the pathophysiological system is operating in a substantially lower stress regime than it was before June 2025. This does not imply zero risk. No pathophysiological system is ever completely risk-free. However, the current state does not resemble the operating condition that existed around 6 months immediately before the stroke. A trajectory interpretation. One of the central principles of viscoplastopology is that trajectories often reveal more information than isolated numerical values, viewed as a trajectory rather than a snapshot. The recent 6-month pattern appears to represent a system carrying residual long-term metabolic memory rather than a system returning to the physiological state that existed before the stroke. The upward shift in post-stroke glucose creates a persistent background influence that remains visible within the slower-moving TSI-3C curve. Meanwhile, the faster TSI-3B curve reflects more recent physiological behavior. The modest separation between these two curves therefore appears to be a natural consequence of the different response speeds of the two indices. Conclusion: the brain consumes roughly 20% of the body's energy. The difference between TSI-3B and TSI-3C during the past 6 months can be explained by a combination of mathematics, physics, and post-stroke pathophysiology. TSI-3B behaves as a fast response variable daily averaged glucose that reflects current physiological conditions. TSI-3C behaves as a slow response variable 90-day moving average glucose that retains approximately 3 months of metabolic memory. The persistent post-stroke glucose elevation of approximately 10% to 11% further contributes to the higher TSI-3C values. The current separation of approximately 2 points between the two TSI indices is relatively small and appears mathematically expected, physically reasonable, and pathophysiologically plausible. Most importantly, the current TSI-3C level remains substantially below the pre-stroke peak observed before June 2025. Therefore, the recent relationship between TSI-3B and TSI-3C is better interpreted as evidence of residual post-stroke metabolic memory than as evidence of a return to the physiological state that preceded the stroke. During the past year, I have learned that stroke recovery is not simply a neurological process. It is also a mathematical process, a pathophysiological process, and an engineering process. The human body continuously records its history within its biological signals. Some variables respond quickly, while others respond slowly. Some changes disappear within days, while others leave traces that remain visible for months. The difference between TSI-3B and TSI-3C provides a small but meaningful example of this principle. Together, these two indices remind us that recovery is not merely about where we are today. It is also about the human body's pathophysiological memory carried forward from yesterday. Understanding both perspectives helps us better understand the trajectory of recovery itself. Epilogue: every 20 to 30 papers, I find myself pausing for a moment of self-reflection. At first glance, this may seem unrelated to the scientific subject being discussed. However, over the years I have learned that periodic reflection is an essential part of the research process itself. When I was about 12 years old, growing up in a rural village in Taiwan, I occasionally walked along the railroad tracks. Walking on a narrow rail requires concentration. One must pay attention to every step in order to maintain balance. Looking too far ahead can be dangerous, but focusing only on the next step is also insufficient. Every so often, the railroad provides a wider section where both feet can rest comfortably on solid ground. At those moments, it is natural to stop, look around, and confirm that the direction remains correct before continuing the journey. My research life has followed a similar pattern. I spend weeks or months studying a subject, collecting data, developing models, testing ideas, and writing papers. Then I pause and ask a few simple questions. Am I still moving in the right direction? Have I learned something meaningful? Am I overlooking an important lesson? Am I using my remaining time wisely? These questions are not signs of doubt. They are part of the feedback mechanism that keeps my journey on course. Looking back across my life, I can see the same pattern repeated many times. I spent 18 years on university campuses studying 10 academic disciplines. I spent 22 years building 8 startup companies, with 7 failures before 1 success. I spent 9 years studying psychology, followed by 17 years studying lifestyle details, biomedicine, chronic conditions, mortality diseases, and human health. More recently, after surviving a hemorrhagic stroke, I have devoted thousands of hours to studying neuroscience and understanding stroke recovery, pathophysiology of human brain, and the mechanisms that govern life itself. The subjects have changed, but the process has remained remarkably consistent. Learn, observe, reflect, adjust, and continue. Fame, power, and wealth have always been secondary outcomes. More accurately, they have served as background noise rather than the primary signal. The central signal of my life's symphony has been survival through knowledge and learning through curiosity. Therefore, this epilogue serves as one of those wider sections along the railroad. It is a brief pause to examine the path behind me and the direction ahead. After doing so, I remain convinced that the pursuit of knowledge is still worthwhile, curiosity is still alive, and the journey should continue. Afterthought. This piece of writing serves as a continuous research note and my personal research logbook, documenting what I have gone through during my medical research journey. It simply records my observations, thoughts, and experiences as they occurred. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.